Okay, Math 352, welcome back. We're up to lecture 11, and today we're going to continue on our topic of linear programming, and we're going to look at one of the main algorithms for solving these things, which is the simplex method. Okay, so we've sort of got a bit of an intuitive feel for how linear programs work now. So what we're going to do is sort of take this intuition today, and we're going to turn it into a practical algorithm that can be used to solve linear programs that are big. Okay, so we're not just going to limit ourselves to things we can draw pictures of now. We're going to come up with a mathematical method of solving larger ones. Okay, this is the kind of famous simplex method. Okay, so we're going to start with a linear program in standard form. Okay, so standard form LP, as we've looked at last week, is to minimize a cost C transpose X subject to some equality constraints and some non-negativity constraints. Okay, so that's our standard form LP. We're also going to assume that A is full rank and also that the rows are linearly independent. Okay, so why do we need to assume that? Well, it doesn't really lose any generality here, because if we assume that the rows of A are linearly independent, it means we've got no redundant equations, or they can't be inconsistent. Okay, so A is therefore m by n with rank A equals m, and m is less than or equal to n. Okay, so just things to bear in mind, whenever we're solving a standard form LP, we're always working with a matrix A that's this shape here. Okay, there we go. So it's always going to be a kind of wide matrix. So always have that picture in your head that that's the type of matrix we're dealing with when we're dealing with a standard form linear program. Okay, so to sort of get started, we're going to define a couple of important concepts. So assume for now that the variables have been written in such an order that the last m columns of A are linearly independent. Okay, so we can always do that just by, instead of writing x1, x2, x3, we could change the order around so that we guarantee that the last m columns of our matrix are linearly independent. Okay, so if we do that, we can partition A and X as follows. Okay, so we're going to write our matrix as A is equal to AN and AB. Okay, so AB is going to be those last m columns, so it's going to be m by m, and AN will be the rest of them. So it's going to have, oops, try that again. It's going to have m rows, and how many columns? Well, it'll be n minus m columns. And likewise, we can write our x in the same kind of way. We can split it up into xn and xb, where xb is in R m and xn is in R n minus m. Okay, I'll call this equation 1. Okay, so that's just a convenient thing that the reason for will become clear shortly. So in these kind of partition coordinates, what do the constraints look like? Well, the constraints AX equals B, they become AN AB XN XB equals B, and we can expand out that block matrix form to give us ANXN plus ABXB equals B. I'll call that equation 2. Okay, so I haven't really done anything here. All I've done is split up our matrix A and our vector X in a particular way so that we can write our equality constraints in this particular form of equation 2 here. Alright, now what we can do, we know that AB is invertible, so one way we can get a solution to this is to make xn equal 0. Because if xn equals 0, all those n minus m entries are equal to 0, then we can just solve this equation ABXB equals B for XB. Okay, so if we set xn equals 0, then equation 2 becomes ABXB equals B, or XB equals AB inverse B. Okay, so what we've got xn equals 0, we've got xb is given by this expression here, so we've found a solution to our set of equations. Don't forget, because we've got that fat looking matrix A, it's an underdetermined system, so there are infinitely many solutions. We've just found one of them. Okay, so the resulting x, which is xn and xb, has n minus m, at least, non-zero elements. So that's what it say, has at least. And is called a basic solution. Okay, so if I'm ever talking about a basic solution, I'm talking about a solution that's got at least n minus m zero elements. Sorry, not non-zero, what am I saying? 0 elements. Okay, so that's my definition of a basic solution. We've got at most m non-zero elements. Okay, and likewise we can give xb and xn names. Xn are the non-basic variables, and xb we call the basic variables. Okay, so we make a distinction between the variables we've set to 0 and the variables that we've just solved for from equation 3. Okay, more generally, so what I did to start with is I rearranged my matrix so that the last m columns were linearly independent. In practice, you don't actually need to rearrange the matrix. All you have to do is pluck out m columns that are linearly independent, and if you keep track of which ones you plucked out, then those are your basic variables. So more generally, we don't need to rearrange the columns. We just store a list B of the indices of the basic variables. Okay, so basically you store, for example, if your first two columns are linearly independent and you're 2 by something, then B might be the ordered set 1, 2, for example. This is also very easy to do in MATLAB. So if you're in MATLAB and you've got yourself a matrix, let's say it's 3 by 8, and you just want to, well, basically you know that, say, columns 2, 5, and 8 are linearly independent, and you want them to be your basic variables. If you want to pluck out that matrix AB, then you just store the index set B in a vector there, and you can get the matrix you want by just taking all rows, that's what the colon is for, and the appropriate columns by an indexing expression like that. Okay, so in MATLAB it's very natural to store these index sets B and N. Okay, so back to what we're doing. Okay, so for example, for a 2x4 matrix, with 4 columns, okay, like that, if B equals the set 1, 3, then AB equals A1, A3, N is whatever's left, 2 and 4, and AN would equal A2 and A4. Okay, and we'll start working with these things in a minute. Okay, so what I've talked about so far is basically a partitioning and how we can find a solution to the constraints AX equals B based on choosing an appropriate set of columns. Okay, so we're going to go back to the linear programming. So we're going to discuss what's called the fundamental theorem of linear programming. Okay, so remember from last week's lectures, we've got an intuition as to what the solutions to LP look like. So our intuition says our feasible region has vertices where a number of constraint boundaries intersect. Okay, so that's just the corners of our feasible region. And what else did it say? We can always find an optimum at a vertex. Okay, so that's sort of what we discussed with our graphical solutions. We sort of got a clear idea in our head that we're always going to be looking for our optimal points at the boundary of our feasible region, and moreover that we can always find an optimal point at one of the corners, at one of the vertices. So, in our context, there we have the following statement. So assume A is full rank. The equivalent statement for standard form LPs is if a feasible solution exists, then a basic feasible solution exists. Okay, so if we can solve our constraints, find a point that satisfies our constraints, we can satisfy them in such a way that at most m of the variables are non-zero. And the second one, if an optimal feasible solution exists, okay, so if our problem does actually have an optimum, then an optimal basic feasible solution exists. Okay, so that's actually really important, because what this means is that when we're searching for an optimum, all we have to look at are basic solutions, basic feasible solutions. Okay, so we only need to basically take sets of m columns out of our matrix A, solve them, check they satisfy the non-negativity constraint, and see whether we can do better or not. Okay, we're just restricting our search to these basic solutions. This is like the problem we had for our graphical solution. We're just restricting our search in that case to the vertices or the corners of the feasible region. This is exactly the same thing, but just in slightly different language. Okay, so this theorem says, oops, let's try that again. We only need to consider basic feasible solutions of the type we just looked at on the last slide when searching for an optimum. Okay, or i.e. we're looking for an optimal basis. Okay, which means set of columns B. Okay, so we're just looking for which set of columns we need to choose that will give us our best solution. So that's basically what the simplex method is about. It says if we've got a basic feasible solution, okay, so that will correspond to a particular choice of columns of A. Okay, if you flick back to this previous slide again, when we're finding this solution in equation 3 here, we have chosen m columns of A in our basis vector B, and we can solve for that and we get ourselves a solution. If it's feasible, then that's a basic feasible solution. What we're going to do is say, okay, well, if I take one of those variables, one of those columns out and replace it with a different one, can I do any better? And if I can, then I'll basically take that step and move to a new basic feasible solution. So let's just make a quick statement about that before we get into doing it. Simplex method says once we have a basic feasible solution, so remember, a basic feasible solution, just to remind you, is a basic solution where all the x's are non-negative. Because that's the don't forget we've got those non-negativity constraints as well. Okay, so once we have a basic feasible solution, we try to improve it. Okay, by improve it I mean lower C transpose X, so lower the cost, by replacing one basic variable with a non-basic one. Okay, so at each step of the simplex algorithm we're looking at replacing one of the basic variables only to improve our cost, and we continue doing this until no improvement to C transpose X to the cost is possible. And that's pretty much all there is to it. It gets a bit complicated in the details, but the basic algorithm itself is really simple. We're just basically hopping around the vertices of our feasible region. At each point we're basically going from one corner to an adjacent one, and we're looking for one that decreases the cost. And if we can't decrease it any further, then we stop, because we must have found the optimum. Okay, next lecture we'll go through some examples of this, which will make it become clearer with a solid example. But for now we're just getting through the theory so that we can have a real clear idea of how to implement it when we do some examples. Okay, so let's just see what we can do here. So I'm going to assume at some point we have a basic feasible solution. I'm going to start writing BFS for basic feasible solution. At some point in our algorithm, okay, so we've done k steps already, we're up to xk, with sets b and n of basic and non-basic variables. Okay, so we compute our xb from the formula we had before. Okay, this will be the kth one, equals a b inverse b, just like we did before. And the cost is C transpose xk, which equals Cn transpose xn k plus Cb transpose xb. Okay, and we know that the non-basic variables are 0, so the cost at this step is equal to Cb transpose xb. Okay, I'll call that equation 4. Okay, so that's the cost at our current point. It's only determined by the non-basic variables because the rest of them are 0 and don't contribute. Note that I've partitioned my cost vector C in the same way as I was doing with my variables in my matrix A before. We want to see what happens to the cost if we start increasing the non-basic variables. Okay, so remember that all the n's are 0 at the moment. We want to say, okay, well what happens if we actually make these non-zero? Will our cost start to go down? And if it does, which way should we go to make it go down the fastest? So, if we change xn, we need to recompute xb. And you can do that from equation 2. So you get that xb, so just remember equation 2 was one more further back. an xn plus ab xb equals b. Okay, so we can always solve for xb. If our xn's are non-zero, we can still solve this thing for xb by rearranging it in terms of xn. So xb will equal ab inverse b minus ab inverse an xn. Okay, so if my xn's are not 0, I can still solve for xb in terms of xn by just rearranging that formula number 2. I can do this because I know my matrix AB is invertible, so that's fine. So the costs can be expressed in terms of xn as well. So what it will look like, C transpose x equals CB transpose XB plus CN transpose XN. Okay, and what can we do with that? Well, we can go we'll basically just plug in this expression for xb and see what we get. B, what else have we got? Plus, we've got a C in transpose xn, and we've also got this component here. xn. Okay, so I'm just plugging in this here for xb, and that's what we get. So now it's purely expressed in terms of xn. And just to simplify our notation slightly, CB AB inverse B, that's just our current cost. So that's just C transpose X of K. Okay, that's the cost we had, the CB transpose XB at step K before we started doing anything to it. And we've also got plus, I'll call this vector here R transpose Xn, where R transpose is equal, R is equal to Cn minus An transpose AB inverse transpose CB. Okay, I'm just taking the transpose of the expression I had in my brackets here. Okay, by the way, my C's on those look kind of capitalish. All my C's I'm drawing here are actually lowercase, just in case you were confused. So this vector R is known as vector of reduced costs. Okay, and that can be equation 5. Okay, so let's have a look at this expression here again. If we increase the xn's, then this expression tells us how our cost changes. We know that xn's start at 0, and they're going to be moving upwards, because we know they can't be negative from our non-negativity constraint. So if we increase, for example, the first non-basic variable, then the cost is either going to go up or go down, depending on whether the first entry of R is positive or negative. Okay, so if the first non-basic variable in xn goes up and R is positive, then the cost will go up too. If it's negative, then the cost will go down. Okay, so we can see which variables are going to reduce our costs by looking at the negative entries of R. If there are no negative entries, that means there's no direction we can go that will lower our objective, and it actually means that we're actually at our optimum solution. Actually. Okay, so R quantifies how much? Each non-basic variable affects the costs. Okay, so if R is all greater than or equal to 0, then no improvement to the objective can be made. And xk is optimal. Okay, so what we've got here, first thing we have here, is we have a test as to whether we've finished our algorithm or not. If there's no direction we can go downhill, no direction that's going to make our cost decrease, then we're actually finished. We've found the optimum of our problem. So equation 5 there is our test for optimality, among other things. If R is greater than or equal to 0, we can't improve C transpose X, and we're optimal. Otherwise, we pick the most negative. Okay, it's not actually the only way to do it, but it's kind of the most common one. In R, and choose to increase the corresponding non-basic variable xe. Okay, so we're looking at, we've decided, just to be sane, that we're only going to increase one of the non-basic variables to make our cost go down, and we're going to increase the one that basically reduces the cost fastest. It's a kind of sensible thing to do, and we call this variable xe, called the entering variable. Okay, because that's the variable we're going to increase, and that's the variable that we're going to put into our basis. Okay, but we're not really quite done yet, because we're increasing xe. If we're going to put a new variable into our basis b, then we're also going to have to take one out. And how do we choose which one to take out? Well, if we go back a bit, if we look at this equation here on the left, if we're increasing our xe, then these xb's are going to change. And eventually what will happen is one of the xb's will drop down to 0. And if we go any further, it will cause one of these xb's to go negative. Okay, so what's going to happen is if we can only increase xe so much until we start violating the non-negativity constraints. So the variable that hits 0 first in our basis is the variable that we're going to get rid of from our basis and replace with our entering variable. Okay, so we're going to take this equation here, and we're going to just replace xn with our xe, so we can lose most of this an here. So if we take xb equals ab inverse b minus ab inverse an xn, that becomes, if we're only increasing just the one variable, equals ab inverse b still, minus ab inverse ae xe. Okay, the other columns of an don't matter because we're only increasing one of the variables. And just to tidy this up, I'm going to call that first thing b hat, and I'm going to call the second part d times xe. Okay, so ae is the column of a corresponding to xe. Now, the variable, so if we look at one of the basis variables, the variable xi for some I in the basis becomes 0 when, we're just solving the equation, when xe equals b hat I over negative di. Okay, so if you just look at what, basically we're looking at one entry of this vector equation here, and we're seeing what value of xe will make the ith entry equal to 0. Okay, so if we look at the ith entry, then basically we just solve b hat I plus di xe equals 0, and solve that for xe, which gives us b hat I over negative di. Okay, so we are interested in the first one. So if we computed this xe for all of the different entries, we're basically looking for the smallest one, because we know if we increase it any further than that, we're going to violate that first constraint. So we're interested in the first basic variable to reach 0. Okay, so the index L of the leaving, I made that blue like before, is that for which b hat L over negative dl is the smallest of those various xe's of b hat I over negative di. Now there's actually one more restriction we have to place on this. If one of these di's is not negative, okay, so just look back at this equation over here. Xb is only going to be heading towards, the relevant entry is only going to be heading towards 0 if the di term is negative. Okay, if we increase xe, the corresponding xb variable is only going to go towards 0 if this term here is decreasing. If it's increasing, we can just increase it however much we like, and we're never going to make xb equal to 0. So we add this extra restriction here in. We're only looking at the d's for which di is less than 0. Okay, if no di is less than 0, which I should give this one a name, 8, then 8 implies that xe, so it should be less than 0, can be increased indefinitely. Okay, and i.e. that our LP is unbounded. If we can just continue to increase this xe indefinitely, reducing our cost as we do so, our LP must be unbounded. Okay, so when we're solving the simplex method, it's at this point here that we discover that our LP is unbounded. Okay, so it does show up at some stage during the process. Okay, so at this point we're almost done. What we have to do is we have to switch, we find this leaving variable L, we then switch it and E in the sets. Okay, so L is going to leave the basis B and E is going to enter it. And reform our new A, B, A, N, etc. and do the next step. Okay, so what we've done is we've increased one of the non-basic variables until one of the basic variables became 0. Because it's now 0, we can treat it as a non-basic one, and so it leaves our basis, and the new non-basic and the entering variable can enter it. Okay, now it can be shown that the new AB is invertible. Okay, so one thing you might wonder is that if you could end up getting a set of linearly dependent columns this way, which would cause your algorithm to break down when you're trying to work out your A inverse times things. Okay, so it shows you can show, and I might get you to later on, is that the new AB that you get in this way by replacing columns is invertible. So that's good. Yes, so that basically is the simplex method. We've noticed that it'll tell us if our LP is unbounded. We've got an optimality condition that comes in near the start of each step. Now there's one other little problem that can arise that we'll look at next week, and that's if one of these B hat i's is equal to 0. If that happens, then basically we can't increase xe at all, because if we do, we start violating the constraints. So what we get is we get xe and the current variable xi are both equal to 0. We can swap them around. That will give us a new basis and a new non-basic set, but it won't have decreased the objective at all. Okay, so what can happen under these conditions, which, like I said, we'll talk about next week, is that we can end up cycling around basis sets without decreasing the objective, and it's possible for the algorithm to return to a basic set that we had before. Now the good news is there is a way around this, which we'll look at next week, and it's just an issue for now to be aware of. So let's just make a quick note about that. It may be that one of the that 1 bi equals 0 with a negative di. Okay, so it gets chosen to be the variable. In this case, xe can't be increased at all, so the objective is not decreased. Okay, so we can still switch the entering and leaving variables to get a new basis. But our objective remains the same. Okay, so it is possible to get back to the same basis set in this way previously used. Set in this way. Okay, and that's not so good, because basically we're just going to go looping round and round and round in circles, and the algorithm will cycle. Okay, this phenomenon is called degeneracy. So the long and short of it is, if you implement the simplex method as I've exactly described it here, I could give you a linear program for which your method would just end up stuck in an infinite loop. Okay, so we need to come up with a way of dealing with that, which we'll do next week. But the good news is it is possible, and it's not actually a problem very often. Okay, so just to sum up, will this method terminate? Well, apart from the cycling case that I just discussed, if our linear program only has a finite number of vertices. So, summary: LP has a finite number of vertices, or basic feasible solutions. Our objective decreases at each step. Therefore, we can't revisit an earlier basis. Therefore, simplex method terminates in finite number of steps. Okay, so long as we don't get that cycling behavior that I just talked about, the simplex method will always terminate in a finite number of steps. In practice, that number of steps is usually pretty small, so simplex method is a very efficient and effective way of solving big LPs. Okay, so next lecture we'll look at some actual hard examples to sort of make these ideas a bit more concrete, and we may look at doing some programming of this in MATLAB. So until then, enjoy your day or evening, and I'll see you back in class. Hope your study's going well.